In the previous video, we had an introduction to solutions, some of their properties, and some definitions. So we're going to continue that discussion in this next video. First question is, how do we know whether a solution is going to form in the first place? Some substances are mutually soluble and some are not, and there's some basic rules that will let us make predictions about those. For example, is carbon tetrachloride and water, is that a soluble combination? Well, at this point you probably have no idea. But it's insoluble. For reasons we'll talk about in a moment, carbon tetrachloride and water will not dissolve in one another. How about ammonia and water? Turns out ammonia is actually very soluble in water. They dissolve quite nicely. Salt and water, probably no surprise. You're all familiar with that. That is clearly a soluble combination. And carbon tetrachloride and iodine. Now that's probably a couple of things you're not extremely familiar with, but those two substances happen to be quite soluble. So the question, of course, is why? What determines whether something will be soluble in a particular solvent or not? The reason that certain substances will dissolve in other substances has to do with the types of compounds they are. Whether they're ionic compounds, polar covalent compounds, or nonpolar covalent compounds, the overall rule in chemistry is like dissolves like. Substances prefer to dissolve with another material that is similar to them. So it's not like the opposites attract things you hear sometimes. In the case of solutions, it's like dissolves like. So let's see why that's the case with each of these four. For example, water and carbon tetrachloride. Water is a polar molecule. In fact, it's got hydrogen bonding, so it's very polar. So water has fairly strong positive and negative poles. Carbon tetrachloride, because it's tetrahedral, is balanced and nonpolar, so it does not have those nice positive and negative charges, so water isn't very attracted to carbon tetrachloride. It's not that water is repelled from carbon tetrachloride, it's just that water likes other water molecules better. The positive and negative poles between two water molecules will attract each other. So the water molecules, it's not that they don't like carbon tetrachloride, it's simply that they love each other. They get much stronger bonds if they simply stay together, and so these substances simply do not mix. And therefore we would call this an insoluble combination. Okay, the next pair we looked at was water and ammonia. Now, ammonia is a polar molecule like water. In fact, they both have hydrogen bonding. So there's a strong attraction between water molecules and ammonia molecules. And therefore, ammonia dissolves in water very nicely because water loves water, but it also loves ammonia. And so it can do just as well bonding with ammonia as it can with other water molecules. And therefore, this pair is a soluble combination. Like dissolves like. Polar goes with polar. The next example we had was salt and water. Now, of course, water molecules attract each other, but they're also very strongly attracted to the positive and negative ions in sodium chloride. The hydrogen end of the water molecule is attracted to the chloride ions, and the oxygen end of the molecule is attracted to the sodium ions. This is true with any ionic compound, not just salt. And because of those attractions, ionic compounds like salt, if they're going to dissolve in anything, it's going to be a polar solvent like water. Ionic compounds don't dissolve in nonpolar substances like carbon tetrachloride because there really just isn't a strong enough attraction. But the attraction between ions and water is very strong. Okay, the last one we talked about was carbon tetrachloride and iodine. Now, these are both nonpolar molecules. Of course, a single element will always be nonpolar, and carbon tetrachloride, it's balanced. The chlorines are all balancing each other out. So these molecules only have what's known as a temporary dipole. So as we talked about in chapter 14, as the electrons are moving back and forth in the molecule, they can momentarily form positive and negative poles. So the carbon tetrachloride molecule can temporarily become polar, so can the iodine. And so for a moment, the two attract each other, then the attraction is gone. Then they get that temporary attraction, it's gone, comes back, gone again, and this goes back and forth. So there is at least a small amount of attraction between nonpolar molecules. Not enough to interest a polar molecule. A molecule like water's not real interested in a molecule that's only polar some of the time. Water prefers to dissolve with something that's polar all of the time. And so two nonpolar molecules like carbon tetrachloride and iodine will dissolve together very well. So let's just summarize the rules then. First rule is polar solutes dissolve in polar solvents. Like dissolves like. And of course, logically then, nonpolar solutes dissolve in nonpolar solvents because, again, they are like each other. And then our final example is ionic substances. An ionic solute will dissolve in a polar solvent because they actually are alike. Ionic compounds have positive and negative charges. Polar covalent molecules also have positive and negative charges. What I mean by the degree of solubility is simply a measure of how much solute can dissolve in a particular amount of a solvent. For example, we can't dissolve 5 pounds of sugar in 200 grams of water. If we try to do that, we'll simply end up with wet sugar. So even though sugar is soluble in water, there is a limit to how much you can put in there. Now, on the other hand, if we had 5 ounces of sugar and 200 grams of water, that would work. The sugar is pretty soluble, and we would be able to dissolve that amount of sugar with no problem. So all substances have a certain amount of solubility. Some things are more soluble than others. Sugar, for example, at 20 degrees Celsius, about room temperature, is quite soluble in water. You can put 408 grams of sugar in a mere 200 grams of water. Now, of course, there's a reason I put a temperature here, because solubilities do depend on temperature, and we're going to talk about that a little more later on. If we increase the temperature to 50 degrees Celsius, the solubility rises to 520 grams of sugar in that same 200 grams of water. Now, each of these solutions represents the maximum amount of solute that you can put in a particular amount of solvent at a given temperature. Both of those solutions are described as saturated solutions. A saturated solution simply means that the solution contains the maximum amount of solute possible. If I put 409 grams of sugar in 200 grams of water at 20 degrees Celsius, I could still only dissolve 408 grams. The other gram of sugar would simply sink to the bottom, and you'd see a little bit of sugar crystals on the bottom of your container. So, at 20 degrees Celsius, if we put 408 grams of sugar in 200 grams of water, we have what's known as a saturated solution. Now let's suppose that we heated the solution up. We take this exact solution and we heat it up to 50 degrees. Is our solution still saturated? Well, according to our information up here, we have room for 520 grams of sugar, but we've only got 408. So we have less than the maximum amount, and therefore this particular solution would be called unsaturated. Now let's continue on. Let's go ahead and take this warmer solution at 50 degrees and add another 112 grams of sugar, bringing it up to a total of 520. If we do that, we now once again have the maximum amount of sugar that you can dissolve in 200 grams of water at 50 degrees Celsius, and so we're back to being saturated again. So saturated is a different amount depending on what your temperature is. Now, For our final step, let's cool the solution back down. Let's lower the temperature back to 20 degrees Celsius. At this temperature, there should only be room for 408 grams of sugar, but we have 520. What should happen immediately is the extra sugar should all crystallize out. We should very quickly find 112 grams of sugar crystallized in a pile on the bottom of the beaker. With most chemical compounds, that's exactly what will happen. But that's not the case with sugar. That extra sugar is going to remain dissolved, and we have now what's known as a supersaturated solution. So a supersaturated solution is simply one that contains more than the maximum amount that's supposed to be possible at a given temperature. Eventually, that extra sugar will crystallize out. It just happens to take some time. Now, there's a fun experiment you can do at home, especially if you've got kids, and that's making rock candy. So we can take advantage of this supersaturated property that sugar has, and we can slowly grow these really lovely crystals. If your kids don't have the patience to wait a whole week for the rock candy to form, here's a fun video by the Sci Guys.
Today on Sci Guys, we're making rock candy.
Welcome to Sci Guys. I'm Ryan.
And I'm Teresa, and today we're making rock candy.
Let's rock out.
Different kind of rock, but that's okay.
This episode is a viewer recommended episode. Thank you to these viewers for the suggestion.
Rock candy is made from crystallized sugar. Crystallization is the process of forming a solid crystalline precipitate from a solution or melted substance.
The equipment and ingredients you're going to need for this episode includes a whole lot of sugar,
A pot,
a tall glass,
a clip or clothespin wide enough to cover the top of the glass,
wood skewers or popsicle sticks,
and optionally, flavoring. The safety equipment you're going to need for this experiment include goggles, thermal gloves, and an apron or lab coat to protect from spills and splashes. Also, because the sugar solution is extremely hot, adult supervision is required.
The first step in our experiment is to make a sugar solution to put on the stove. Add 1 cup of water to your pot. Then 3 cups of sugar. Mix them all together until they're thoroughly mixed.
Next, take one of your skewers and dip it in some water, and then roll it in sugar. This will create the seed crystals for a rock candy. Once it's coated, set it aside until it's dry.
While you wait for your sticks to dry, place the pot that contains the solution onto the stove and turn the stove up to high. Continue to stir your solution as it warms up. Once your solution begins to boil, stir it rapidly until all the sugar has been mixed into the solution. Once all your sugar is mixed in, this is a great time to add any flavoring or coloring. Once you're done mixing in all your sugar, colors, and flavors, remove it from the burner. The next step in our experiment is take your boiling solution and pour it into the glass in which you're going to grow your crystals. Let the solution cool for 10 minutes, and then place the sugar-coated stick into the middle of the glass and hold it in place with the clip. Leave your solution in a warm, dry place to cool. As it cools, crystals will begin to grow on the stick. The process of growing these crystals can take a couple of days up to a couple of weeks. Check your crystals daily and make sure that the crystals growing on the stick don't come in contact with any crystals growing on the sides or bottom of the glass. If you notice they're growing close together, reposition the stick so it's further away from other crystals. Once your crystals are done growing, use a knife to crack the top shell of your solution. Gently remove your crystals from the solution and hang them in a new glass using the clip to hold it in place to drip and dry. Once your crystals have finished dripping and drying, you'll have a delicious, crystalline, sugary snack. During the filming of this episode, we tried using Kool-Aid for flavoring and coloring. We had limited success and the crystals grew quite small. We think the sucralose and other additives inhibited the growth of the crystals on the sticks. When we repeated this experiment using food coloring and liquid flavoring extracts, we had greater success in growing larger crystals. To get a lighter color, we used 10 to 15 drops of food coloring, and for the darker color, we used around 50 to 60 drops.
We've been talking about supersaturated solutions, and we discussed rock candy and how you can make a supersaturated solution of sugar, but over time that extra dissolved sugar will slowly crystallize out and form that candy. However, it takes quite a while. Even when I do my special method with the sugar and I put some sugar crystals on the string in the rock candy, it still takes a matter of hours for it to happen. The absolute best supersaturated solution you can get is sodium acetate. Sodium acetate dissolves in water to the tune of about 90 grams of sodium acetate to every 10 grams of water. So it's extremely soluble in hot water. So you heat the water up to maybe 80 degrees Celsius, you can dissolve a lot of sodium acetate. When the solution cools back to room temperature, all that extra solid should crystallize out, but it doesn't. These are solutions of sodium acetate, all supersaturated solutions. They are very stable, unlike sugar, which after a week or two will begin to crystallize no matter what you do. Sodium acetate, as far as I can tell, is permanently stable. I last used these test tubes back in May. It's now the end of October. It's almost November. And these have been sitting in my cupboard since then, and they will probably continue to sit there for as long as I want. So let's take a look at what happens if we add a crystal of sodium acetate to one of these test tubes. I'm going to take one little crystal here on my finger, and let's drop it in that liquid. The instant we do that, the sodium acetate begins to solidify. It is crystallizing so quickly, the liquid can't even run out of the tube. Sometimes if you get a little air bubble to go up there, it'll start crystallizing from the top. But eventually, that entire tube is going to solidify. Now, based on the things we've been talking about in chapter 15, what's the one word we would use to describe this process? Answer, of course, should be spontaneous. This process occurred spontaneously. I always ask my students at this point in time to tell me what the test tube feels like. Is it warmer than it started? Is it colder? Or is the temperature the same? Why don't you guys think to yourselves, what do you think has happened to the temperature? Has it gotten hotter, colder, or has it remained the same? I can tell you that the most popular answer I get is that the test tube has become colder. And that's because it looks like ice. It looks like it froze. But if you think about it in terms of energy and entropy. Entropy does not like this process because it formed a solid from a liquid. So entropy is going to say thumbs down. Yet it happened anyway. The only way this could be spontaneous is if somebody wanted it to happen, and that somebody has to be energy. So the only way that this could occur spontaneously and have entropy decrease is if energy is released. And I can tell you that this test tube is very, very warm. It's quite toasty. They use this same solution in chemical hot packs that hunters and such use, and fishermen when they're out in the cold, they want to warm their hands and feet up. You put a little plastic pouch of this in your gloves or your socks, and when it solidifies, it produces a lot of heat. Let's go ahead now and see if we can actually measure this temperature change as the solution solidifies. As you can see, before we've added a crystal to a fresh test tube of the supersaturated solution, the temperature on the thermometer is about 22 degrees Celsius, and the test tube, of course, should be at the same temperature because it's been sitting in the cupboard for the last 6 months or so. Let's go ahead now and put the thermometer into the solution and add a crystal. All right, let's go ahead and add a crystal to the test tube and see what happens to the temperature. As you can see, the crystals immediately begin to form in the test tube. As soon as the crystals reach the bulb of the thermometer, we should see an increase in temperature. And there it goes. The temperature begins to rise very rapidly. There's 35. Now it's reached 40 degrees. There's 45. And we're closing in on 50 degrees. So that's about the temperature of hot water. So we had predicted that for this process to take place spontaneously, since there's a decrease in entropy when we form the solid, we should see a release of energy, and the increase in temperature confirms that that is indeed the case. Let's go ahead and do this one more time. This time we'll use a much larger test tube, and we'll zoom in so you can get a better view of what's happening. Go ahead and add that crystal again, and you can see the crystallization begins to happen very rapidly until it moves all the way down the test tube. Very cool. Now this is a fun variation on the demonstration. What I'm going to do this time is I'm going to pour a solution of the supersaturated sodium acetate onto the tabletop. So watch very carefully. There was a crystal already on the countertop, and as soon as the solution hit it, it immediately began to crystallize. If we're very careful, we can make a pretty tall column of the sodium acetate. Oh, that's a pretty good one. And as you can guess, lots of heat radiating off of that. There are a couple of factors that can have a pretty significant effect on solubility. The first one of those that we've talked about a little bit already is temperature. When we were talking about sugar just a couple of minutes ago, we found that temperature did have a pretty significant effect on the solubility of sugar. So for solids, the general rule is that increasing the temperature will increase the solubility. That's not always true, but most of the time. There are some rare exceptions where increasing temperature actually makes a solid less soluble, but that's very uncommon. So let's take a look at a hypothetical crystal of sugar. If we add that sugar to water, in order to get the sugar to dissolve into the water, we have to break the bonds between the sugar molecules. If the temperature is fairly low, then it's more difficult for the sugar molecules to break apart. It takes energy to break those bonds. So at a lower temperature, we're not going to be able to get as much sugar to dissolve into that water. On the other hand, if we increase the temperature, that additional energy helps to break those bonds, and now we get more sugar dissolved in the water. So for sugar and almost all solids, that additional energy helps to break the bonds between the molecules and allows us to dissolve more solid in a given amount of liquid. Now, temperature also will affect the solubility of gases, but it's actually the opposite direction. increasing temperature actually decreases the solubility of gases. And let's take a look and see why that is. When a gas is dissolved in water, the gas molecules, remember, are already separated from each other. That's the nature of gases. So when you have something like a solid like sugar, the first thing you have to do is break the particles apart. Well, in gases, that's already been done. So the gases can readily dissolve into the liquid, and the gas particles form bonds or attractions with the molecules of the solvent. In order for the gas particles to escape from the liquid, they need energy. If we keep the temperature colder, then it's more difficult for the molecules to escape. That's a good reason, if you're opening a can of Pepsi or Coke or whatever soft drink you prefer, if you keep it colder, it will remain carbonated longer. At a low temperature, it's harder for those carbon dioxide molecules to get enough energy to break the bonds with the water and escape. If your soft drink is warmer, then the molecules have more energy. So if you warm it up, now with that extra energy, it's easier for the molecules to escape into the air, and your carbonated beverage is going to go flat faster. It's the same reason that fish like trout and salmon like to live in cold water. In cold water, many more oxygen molecules dissolve in the water, which the fish need to live. In warmer water, if the water gets too warm, fish like trout can't survive. If it gets above, say, 70 or 75 Celsius, at 90 degrees Celsius, those trout would die. There is just simply not enough oxygen in the water for them to live. So it's the opposite of what we saw for solids. With solids, increasing temperature increased solubility. For gases, increasing temperature decreases solubility. The second property that affects solubility is pressure. Now it turns out with solids, they're essentially unaffected by pressure. Pressure has almost no effect on solids for a very simple reason. Solids already have their particles, molecules or atoms or ions, packed tightly together. So putting pressure on, say, sugar has no effect on it. The molecules are already touching each other. They cannot get any closer. So pressure really has no effect on the solubility of solids. On the other hand, it's a different story for gases. Gases are mostly empty space. So increasing pressure actually will increase the solubility of gases for a very simple reason. If we have a fairly low pressure, represented by just a few molecules of gas above our beaker, the molecules in the air are moving into the liquid and dissolving, but at the same time, gas molecules from the liquid are leaving. And they reach that state we talked about previously called dynamic equilibrium. Now, if we were to increase the pressure of gas, say we doubled the number of molecules of gas above the liquid, now they're entering the liquid twice as fast. So they're slowly going to build up more molecules in the liquid until eventually we get this balance once more. But because we doubled the pressure, once we achieve dynamic equilibrium, there's going to be double the number of molecules dissolved in the liquid. And so gases are more soluble at higher pressure, and solids are essentially unaffected by pressure. Soft drinks, as we mentioned earlier, are a good example of this. They put a lot of pressure of carbon dioxide above the liquid in the soft drinks. So all those CO2 molecules up above the Pepsi or Coke or Fanta or Sprite are hitting the surface of the soft drink and they're dissolving. And the more molecules you pressurize in that can, the more of them are dissolving in the liquid and the more carbonated it will be. Of course, as soon as you open the can, out comes the pressure and the molecules begin to escape from the liquid and eventually the soft drink will go flat.